Hi, welcome to this short video. In it, I'm really just going to do a square wave voltammetry experiment and sort of use that experiment to sort of discuss why I really love square wave voltammetry. I think I like square wave voltammetry probably even more than I like EIS. And when I say I love square wave voltammetry, I actually mean in the context of biosensors and electrochemical assays. There's something about, not something about square wave voltammetry. It's not mysterious. It just gives us such good signals and so many handles to kind of essentially play upon. So the first thing I'm going to do is I'm just going to grab some of this reagent from ZP. So this is a ferricyanide solution. I'm just going to put actually I've got it already decanted. I'll just put 50 microliters onto the sensor. The first thing I like about electrochemistry and especially the way that we do electrochemistry is because we haven't optimized this, but this is only a 50 microliter drop. So you kind of, it's a great science for doing sort of point of care, point of need diagnostics because the sample size is quite small. Next thing I'm going to do is I'm just going to give this file a name. So I've called it Square Wave Voltammetry 5 millimolar because that's a ferricyanide solution I'm using, and I've just called it number 2 so I can find it, and I've put sample cluster as a demo because that will allow me to find the data easier later on. Now I'm just going to go continue. I'm going to start the experiment at minus 400 millivolts. I'm going to go to a end potential 600 millivolts. My voltage steps is 1 millivolt. My current range is 100 microamps. My amplitude is 40 millivolts and my frequency is 30 hertz. What I like about that is there's a few unique parameters in there as regards to something like square wave voltammetry. Sorry, not square wave, but cyclic voltammetry. The fact is I've got amplitude and frequency. So I feel like square wave voltammetry is kind of that kind of hybrid between linear sweep voltammetry and EIS, electrochemical impedance spectroscopy. In EIS, you do have then frequency, which can also vary. Do you always need to do that? Probably not. So I do like square wave voltammetry, and I'll just do the experiment really to kind of illustrate, why I like it. Now, what I like about this potential stat as well is I can already see that I'm going to get a nice signal because I can see, the oxidation wave for that. What's happening is we started off at about minus 400 millivolts, so we produced we actually reduced ferri to ferrocyanide, and then we reoxidized it in the actual sweep then. So that's why I get a wave for it. What it then says is uploads complete, and I can actually share that now with whoever I so wish. Which is off that app, but upload complete means if I just go back to the screen here, that the actual data has actually gone into Julie. So I'm just going to do a quick refresh here. This is something that's very powerful about this system, that in fact I'm able to do that experiment, very small scale, very easily, no cables on a screen printed electrode. I get a nice looking data, and then upload complete means that actually the data went to the cloud. So there's no question as to where my data really is. It's always automatically saved up here. And then there's a very powerful set of tools for actually interpreting the data. So here's my signal. This is what I kind of saw appearing on my phone in real time. But I can go into here and I can... so I've got... what I can do here is I can see here that what I'm looking at here is actually the difference. So I haven't explained square wave voltammetry, but there's two almost signals behind square wave voltammetry. There's the forward scan, there's the forward, and there is the reverse. So I'll show you what those look like now. So if I just go into tools and I go here, let me just have a quick look. And I'll go general. I'll just add VD1, or just VD, and I can see that that's the forward. And then if I go here and go VD1 here, I'll make sure that I choose the reverse here. So let's just have a quick look at what that looks like. So I can always go back and see. So I can see my difference signal. That's my forward minus from my reverse. I can see my forward, and I can also see my reverse. So the difference is basically, I mean, it says it in the thing, it's the difference between the forward and the reverse scan, but it kind of tends to enhance my actual overall signal. So I got a really nice, clean signal there. What I can also do, what's very powerful about this system as well, is I'm just going to turn off this for a second and just go down to, I'll just turn this off as well. I can actually turn that raw signal, let's say I go to VD1 here, I'm just going to say show extracted values, and I'm going to find the peak height. Now I'm going to look for the peak height at about 200 millivolts, and I'm going to put a window around that 100 millivolts. This is why this system is very cool, see, because if your peak shifts around a little bit, it doesn't matter. We can still find the peak height. So there we are. I found the peak height here, but at the moment I don't have the concentration. But let me just show you something really cool, because it allows you to go from the idea of peak height to an actual concentration really quickly. So I'll just put it in 10 here, and I'll put in 0 here. This is like trying to fit a linear equation with a gradient of approximately 1/10 with an intercept of 0. Let's have a quick look what that looks like. And let me come down, and yeah, so in fact it says at the moment that's 10 millimolar. So let me just do something, let me just show you how in real time I can actually edit this up, and then I can put 20 in there and have a quick look what that looks like. So at that point now it says about 5.4, so I can 5.4 millimolar, and the true concentration is actually 5 millimolar, but I can really tune that up and then actually return 5 millimolar. So the reason I like that was just, the last bit there was just really talking about features of Joule. But what I really like about Square Wave Voltammetry is you've got 2 extra parameters. You've got the amplitude, which you can optimize on, and you've also got the frequency. Now I use an amplitude of 40 millivolts, and I use a frequency of 30 hertz. Those are just kind of the default values that came with the Sensor All Potentiostat. And then I actually like the fact that you do actually have, you can look at the different signal, the forward signal, or the reverse signal. Because at ZP, we're real pragmatists, actually, and we actually just want to find the signal that often gives you the lowest limit of detection, and mostly and the highest sensitivity. So we're always balanced. There's always a balance in life. But I do like the fact that we do have these extra levers in Square Wave Voltammetry as opposed to linear sweep voltammetry or cycling voltammetry. So that's why I'm particularly a fan of Square Wave Voltammetry. Now, if you do have any technical questions, don't hesitate to reach out to us on the ZP website. Okay, thanks very much.